All right, folks, good morning and welcome to Analog Electronic Circuits. This is lecture 3. In the last class, we basically saw how one can handle networks with two terminal elements which are nonlinear. Today, we will look at the other class of elements that we see, namely two ports, right, where you have a two port network which can potentially be nonlinear. But before that, let me quickly review two port networks which are linear. So, let us say you have a box, a linear network with two ports, and of course, I mean there could be a whole lot of stuff inside, you do not know what is inside. However, as far as the outside world is concerned, you have just access through two ports, and there are many ways of describing this the behavior of this box as far as the external world is concerned. And I mean you have seen this in your prior classes, and what comment can you make? I mean, how can we model this this linear two port? Okay, if you have a two terminal network, a box with two terminals, as far as the external world is concerned, how can we model this linear two terminal box? You have a linear two terminal box, right? A box with two terminals coming out, you are told it is linear, it does not have any sources inside. How can you model this this box? It's a you model it as a resistance, right? Assuming there is no memory inside, you basically can model it as a resistance, right, as a linear resistor. All right. Now, if you have a two port with two pairs of terminals coming, how can you model it? Yeah, I mean you already learnt in your earlier classes a variety of parameter sets that can be used to describe the behavior of this two terminal or this I mean this two port network as far as the external world is concerned, right. All of you, have you heard of the parameter sets that are, what are the commonly used parameter sets that are used to describe a linear two port network? Yes, you. Are you familiar with this or you are not? Huh? Okay. So, what are the commonly used two port parameters? The admittance parameters, the impedance parameters, the scattering parameters, the the hybrid parameters, and all sorts of stuff. We can take any one of them. They are all equivalent, as you know. You are given one set, you can actually derive another set. The algebra may be involved, but otherwise it is straightforward. Okay. So, let us take for example the y parameter set. So, when you describe a two port network using y parameters, what are the independent variables and what are the dependent variables? V1 and V2, the port voltages are independent, and the port currents are dependent. All right. So, and because it is a linear network, the port current I1 is a linear function of V1 and V2, and the constants of proportionality therefore have to have dimensions of admittance, right. So, that is basically V1 plus Y12 V2, I2 is Y21 V1 plus Y22 V2. Okay. And how will you find, given a box, how will you find say Y11? Yeah. So, Y11, as you can see from these equations, is nothing but I1 over V1 under the condition that V2 equal to 0. And when you say V2 equal to 0, what is it? It is a short circuit. So, these are therefore called short circuit admittance parameters. Does it make sense? Okay. Similarly, y12 is nothing but I1 over V2 when V1 equal to 0. So, y11 is the admittance seen at port 1 when port 2 is shorted, and similarly y22 is the admittance seen at port 2 when port 1 is shorted. And what does y12 quantify? Y12 quantifies the effect of a voltage excitation at port 2 on the current, the short circuit current in port 1, and likewise y21 quantifies the short circuit current in port 2 when you apply a voltage V1 at port 1, correct. Okay. So, as they say, a picture is worth 1,000 words. I mean, whenever you draw, whenever you write equations, it's it's often quite useful to draw a picture. But of course, if you had only a box with 2 terminals, drawing the picture is easy. What is the what picture will we draw if we want to demonstrate its characteristics? If you have a 2 terminal element, what picture will we draw to demonstrate its characteristics? We just draw, it is a linear. If we further assume that the 2 terminal box is linear, then there is neither the characteristics of that box are nothing but you plot I versus V or V versus I. Okay. Now, what comment can we, if we want to show these equations graphically, what do you think we will do? Okay. Okay. So, so clearly I1 is a function of 2 variables V1 and V2, and to show this I1 graphically as a function of V1 and V2, we would have to draw a 3D plot. Unfortunately, the paper is only 2D, and therefore, you fix one variable. So, so what we do is basically say I will plot I1 as a function of V1 for several values of V2, correct. And if I do make such a plot, what will I get? So, for let us say for V2 equal to 0, what will you get? You will get a straight line passing through the origin. So, just for argument's sake, I am going to draw a line like that. What is the slope? What is the slope of this line? The slope is nothing but y1. Okay. Now, so this corresponds to V2 equal to 0. Now, for V2 say is equal to 1 volt, what do we see? It will be the resulting so called curve will be parallel to this line, except that it will be either shifted upward or downward depending on the sign of y1, right. So, V2 equal to 1, V2 equal to 2, all right. So, and what are the so for various values of V2, you will get a family of curves. In this particular case, because the 2 port is linear, there will be a family of lines where the spacing between the lines will be identical for identical increments in V2, all right. So, this therefore is going to be y12. Does it make sense, people? Okay. So, these are what are called the, I mean, typically in this part of the world we write from left to right. So, whenever we have a 2 port, I mean, one port is the input and one port is the output. So, which port do you think will be the input? Yeah, basically the stuff flows like this in this part of the world. So, the left port is called the input port. So, since these curves capture the behavior of the input port, these are what are called the input characteristics of the 2 port, right. So, in other words, rather than giving out y11, y12, y21 and y22, we might as well supply the user with these with this picture, right, and from this from the input characteristics, what all can the user infer? y11 and y12, all right. Okay. So, now the obvious thing is what other characteristics do we need to draw? Well, analogously we have the output characteristics, which basically have we plot I2 versus V2 for different values of V1. So, again I do not know, I am just going to draw some pictures. So, this is going to pass through the origin. So, this is for V1 equal to 0, and what is the slope? Slope is y22, okay, and again you will get a family of lines which are parallel to each other, and so say V1 equal to -1 and say V1 equal to 1, okay, and okay, and again the slope, all these lines are parallel to each other, and for equal increments in V1 there will be parallel, the distance between these two the lines, adjacent lines will be identical. Okay. So, these are the output characteristics. Right. Another way of depicting the same 2 port, right, not in graphical form, but in circuit element form or like a network, is to how do we I mean, how do we express these in terms of network elements? Basically, you can draw, you can represent these equations in this form. So, this is y11, and what should we do? Is y11 an admittance, or is it a resistance or a conductance? It is a conductance. Then what? What kind of current source? It is a voltage controlled current source, and must it flow down or must it flow up? Down. And what is the value of that voltage controlled current source? Yes, y12, V2, and similarly port 2, this is y21 times V1 and y2. Does it make sense, people? All right. So, the next question I would like to ask you is, how many terminals, what is the minimum number of terminals needed to make a 2 port network? You need 3 terminals, because one terminal can be shared between the input and output ports. Okay. in that case, then what happens is that these two terminal nodes will be the same, and this will be for a 3 terminal 2 port. Is that clear? All right. Having refreshed our memory about linear 2 ports, now let us consider the simplest case of what happens when the 2 port is nonlinear. When I say the simplest nonlinear 2 port, it also has 3 terminals, okay. And so we apply some voltages at the ports and some currents result. So, which are the independent variables and which are the dependent variables? The way we have drawn it, voltage is independent and the currents are, this is exactly the same thing that we did with the linear 2 port, right. I mean, there is no need, there is no nothing holy about using voltages as independent variables. We could have as well used currents as independent variables, in which case the voltages will become dependent. But since we chose to go that way for the linear 2 port, we will also do that for the nonlinear 2 port. So, now what comment can we make about I1? It is a nonlinear function of some function f of V1 and V2, okay. And similarly, I2 is a function of, is some other nonlinear function g of V1 comma V2. Correct? And so, if you embed this nonlinear 2 port in a bigger network, correct, what comment can we make about finding the branch voltages and the currents? SU? Huh? Yeah. So, to basically if you embed this network, this nonlinear 2 port in a larger network, like we discovered in the case of 2 terminal nonlinear elements, the Kirchhoff's voltage and current laws will become coupled, a set of coupled nonlinear equations, and that is just as difficult to solve as in the previous case, and therefore, we have to resort to a numerical solution, right. However, if we increased the exciting terminal voltages by small amounts, right. Okay, what comment can we make about the currents? They will also change by small amounts, and again we will come back to this definition of what small means, but at this point let us assume that they change by small amounts. So, consequently, what comment can we make? I1 plus small I1 is function of V1 plus small V1, V2 plus small V2, and similarly I2 is G of V1 plus small V2, okay. So, if you subtract these two equations, what do you get? What can we say about I1, small I1? We can simply expand the second equation or the equations on the right in the following way. Capital I1 plus small I1 is nothing but f of V1 comma V2 plus partial derivative of f with respect to the first argument evaluated at V1, and again I am going to abuse notation and basically say that this times V1 plus partial derivative of f with respect to the second argument evaluated at V2 times V2, and likewise I2 plus small I2 is approximately g of V1 comma V2 plus dou g dou V1 times V1 plus dou g dou V2 times V2, all right. And this of course we know to be, what is that quantity? What is f of V1 comma V2? That is nothing but I1. Similarly, what is g of V1 comma V2? I2. Correct? So, therefore, this guy and that guy go away, likewise those two terms go away, and what do we have? Small I1 is dou f by dou V1 times V1 plus dou f or dou V2 times V2, I2 is dou g by dou V1 times V1 plus dou g over dou V2 times V2. Does it make sense, people? Okay. So, in other words, we can write the incremental changes in the currents as in matrix form as comma V2. Are these linear or nonlinear? These are a set of linear equations where even though the two port is nonlinear, right, for small changes in the exciting voltages, the changes in currents can be related to the changes in port voltages using a set of linear equations, right. Again, this is not much of a surprise, this is exactly what we saw in the one terminal case. In the one terminal case, the IV characteristic of in general is nonlinear. Around the operating point, we were able to approximate the curve by a straight line, correct. Now, capital I1 is a function of V1 and V2. So, it is basically a surface in 3D, right, and around an operating point we are approximating the surface by a plane. Okay. So, these are linear equations. And using our experience with the two terminal nonlinear element, where we called the ratio of the change in current to the change in voltage as, what did we call that? The incremental conductance or incremental admittance. Now, what are we going to call this matrix? Earlier we called it the admittance matrix or the Y matrix. Now, we should call it the incremental Y matrix.